Hello everyone, my name is Yue Wang and I'm a PhD student from Peking University. It's my great honor to share my research entitled Enhancing Large Language Models with Staged Grouping and Dehallucination for Header File Decomposition. First, let's look at the problem background. We have identified God header files, a newly discovered code smell that refers to header files with large code size and wide file impact. These files are included by numerous other code files, and modifying them results in recompilations that take a very long time. For example, this file guc.h contains over 500 code declarations. Each time it is modified, nearly 400 files that included directly or indirectly have to be recompiled, involving more than 700,000 lines of code. Our previous empirical study found that about 37% of open-source C projects are affected by such God header files. So how do we solve this? Decomposing God header files into several smaller files is an effective way to mitigate their negative impact. But currently, existing decomposition approaches mainly rely on code similarity metrics, which often fail to capture functionalities accurately, leading to low developer acceptance. Since large language models are trained on extensive code repositories authored by real developers, they may demonstrate a human-like code understanding and generate suggestions that align more closely with those performed by developers. To explore large language models' strengths and limitations on header file decomposition, we conducted a preliminary study, applying traditional decomposition approach and two large language models on 153 real-world header files. This table presents the result. The right columns show how close the generated decompositions are to those conducted by human developers. You can see that LLM suggestions are indeed more consistent with actual developer operations. But there are also three critical limitations. First, LLMs have difficulty handling lengthy code file inputs. The two models failed to generate output on 1 and 7 lengthy files respectively. Second, LLMs suffer from hallucinations. Their decompositions often contain spurious or missing entities, and more than 2/3 of the decomposition results are incomplete. Third, there are still cyclic dependency issues in the decompositions, which may lead to compilation errors. To solve these problems, we designed a new approach with two-stage grouping framework, factual knowledge enhanced prompts, hallucination detection and correction, and cyclic dependency resolution. Here is the overview of our approach, HF Decomposer. Our approach works in 5 main steps. First, we pass the input file to extract code entities and their relationships. For lengthy files, we perform initial grouping to handle token constraints. Second, we construct a factual knowledge enhanced prompt and require LLM to generate a decomposition plan. Third, we detect and correct hallucinations by removing spurious entities and reassigning missing ones. Then, we resolve cyclic dependencies and automatically execute the refactoring. Now, let me explain each step in detail. In the first step, we extract code entities, macros, data types, variables, and functions. They cannot be further decomposed. We consider 4 key relationships: dependency, invocation, semantic similarity, and positional distance. For lengthy code file input, we employ a two-stage grouping framework. We initially cluster related code entities using traditional similarity metrics, then leverage position relationships to split non-consecutive clusters into smaller consecutive ones. Each group is then summarized by the LLM for compact representation. Next, we construct a factual knowledge enhanced prompt, including instruction, a decomposition example, code file content, and factual knowledge. For normal files, the content is the full file. For lengthy files, it's the group summaries. The factual knowledge includes a code entity list to mitigate missing and spurious entities, plus dependencies and invocations to enhance code comprehension. We use the prompt to require the LLM generate decompositions. However, hallucinations cannot be fully eliminated, so we also perform error correction. For spurious entities, we simply remove them. For missing entities, we calculate their similarity with each subheader file and assign them to the file with the highest similarity score. After correction, cyclic dependencies may still exist. Our heuristic algorithm fixes these by evaluating different moving options. For 2-node cycles, we calculate a moving gain for 4 possible solutions and select the best one. Longer cycles are iteratively reduced to 2-node cycles, processing the longest first to ensure termination. Finally, our approach automatically executes the refactoring, generating file content for each subheader file and updating include statements in all affected code files. Now, let's look at the evaluation. We designed 3 research questions. First, can our approach address LLM limitations and outperform existing approach? Second, how effective is our 2-stage grouping framework? Third, how does each component contribute? The evaluation dataset is mined from commit histories of top 100 C projects from GitHub by star count. We adapt refactoring miner to identify header file decompositions and filter out cases involving substantial functionality modifications. We split the dataset by entity count. Files with fewer than 200 entities go directly to the LLM, while larger files use 2-stage grouping framework. For RQ1, the overall performance. Our baseline includes the traditional state-of-the-art approach, WAS approach, and 2 leading LLMs, GPT-4o and DeepSeek V3. We can see from the table that, first, through initial grouping, we enhanced the LLM's processing capability for lengthy inputs, achieving a 100% completion rate. Second, factual knowledge enhanced prompts reduced the hallucination rate by over 90% and cyclic dependency issues by 38%. Our hallucination detection and correction module completely eliminates all remaining hallucinations in final results. In terms of decomposition accuracy, we achieved an 11% improvement over the state-of-the-art approach. For RQ2, we verified that initial grouping generates clusters with 98% accuracy, enabling LLMs to handle previously unmanageable input lengths while achieving high decomposition accuracy. For RQ3, ablation studies showed that all 3 types of factual knowledge have beneficial impacts. Among them, entity knowledge is most helpful in reducing hallucinations, while dependency knowledge helps reduce cyclic dependency issues. Both hallucination correction and cyclic dependency resolution ensures reliability and usability of the final result without compromising accuracy. This case illustrates the impact. Without dependency knowledge, the LLM incorrectly assigns the right entity to the left subfile, creating a cyclic dependency. In conclusion, this paper introduces HF Decomposer, a hybrid approach that enhances LLMs with stage grouping and dehallucination techniques for effective header file decomposition. Future work will support customized decomposition requirements based on different developer perspectives. That's all. Thanks for your attention.